So our next talk will be given by Hayne, and the title of their talk is Polar Night Vision at the Moon's South Pole, the Lunar Compact Infrared Imaging System. So Paul, please go ahead.
Okay, thank you very much. So thanks to the session chairs and also to the conference organizers, especially Ricky and his team. I think, as much as we all miss seeing each other in person, this is about as seamless as a virtual conference can be. So thanks a lot for that. So I'm going to talk about the Lunar Compact Infrared Imaging System, or L-CIRiS. Here's the team based at the University of Colorado's Laboratory for Atmospheric and Space Physics, or LASP, and Ball Aerospace, as well as our science team members. So L-CIRiS is a thermal infrared radiometer. I'll describe the instruments in more detail in a minute. This was selected through NASA's L-CIP, or the Lunar Surface and Technology Payloads program, to fly on the CLPS 19C mission. The lander provider is Mast and Space Systems, and our launch was recently pushed to November of 2023, with surface operations in December of that year. I'll talk about the potential science at the landing site, which will be in the South Polar region at a latitude higher than 84 degrees south, and that's still being sort of negotiated, but we do have a notional landing site. So you can see there's a range of different really exciting instruments on this payload. And among those is a thermal infrared camera called L-CIRiS, and that's positioned here on the side of one of the lander panels. And we expect to operate on the lunar surface for about half the month during the daylight hours. So the science background for L-CIRiS is that we've established, through both remote sensing of the moon and other planetary bodies, including the Earth, the value of thermal infrared remote sensing. So temperature is the primary quantity that we seek to measure with an instrument like Diviner, which is shown in the upper right. Diviner also has shown the way that you can use multiple spectral bands in the thermal IR to do compositional analysis, specifically looking at the silicic or mafic content of the surface materials. And then, of course, the physical properties like density that kind of get folded up into thermal inertia. So that's the types of measurements that get made with thermal IR remote sensing. And I think what Diviner has shown is the need for something like L-CIRiS on the lunar surface. And so what we found through Diviner is this extraordinary thermal diversity, which is arguably larger on the moon than anywhere else in the solar system, from less than 30 Kelvin up to more than 410 Kelvin in the lunar pits. And then compositional diversity, things that we didn't necessarily anticipate, like the silicic domes, and then thermophysical diversity, showing the progression or evolution of fresh craters evolving to older craters as the rocky material gets broken down into regolith. And we can, sort of watch this happening, before our eyes effectively through looking at craters of different ages. So this is sort of the background science that shows that there's this extraordinary diversity that you can even see at the orbital scale. L-CIRiS has 3 different science objectives, and I'm going to go through each one of them. So the first objective is to provide ground truth for the compositional investigations like those done by Diviner. So here's an example of a map provided by Ben Greenhagen of the Christiansen feature on the moon, again from Diviner data. You can see this striking variation in the composition of the lunar surface. We know that there are effects that go into this that have been corrected mostly empirically, and those include surface roughness as well as near surface thermal gradients, basically. And so we've done these sorts of corrections empirically based on what we observe with Diviner. With an instrument down on the surface deployed, taking data at much higher resolution, you could do this using a physical model. So we hope to be able to use the L-CIRiS data from the surface to then better understand what we're actually seeing in the Diviner data. So we anticipate this kind of feed through or feedback on the Diviner data to improve these global maps, as well as those as well as those of other instruments like M-cubed in correcting for surface roughness and those other effects in the thermal infrared. And so the three compositional bands for L-CIRiS overlap with both Diviner and Lunar Trailblazer. Those are shown on the right-hand plot with the emissivity spectra for different compositions that we anticipate to measure on the surface. The second science objective is related to the first, which is to get down on the surface and directly measure the thermophysical properties at the lander and rover and astronaut scale for the first time. We don't actually know what the thermal inertia of rocks on the moon is. When we develop these models to produce rock abundance maps from data sets like Diviner, we basically assume a thermal inertia based on our best knowledge of the composition and density of the rocks. But L-CIRiS will actually, for the first time, directly measure the thermal inertia of the rocks and the regolith separately, again, feeding back to the Diviner data so we can produce even better global rock abundance maps from Diviner. Third objective is near and dear to my heart, which is the micro cold traps question. Do these things actually exist and what are their temperatures? You'll hopefully see from other talks and posters, both during this session and even in the coming months and years, that other instruments on this same lander, as well as Viper, will directly measure the composition of these micro cold traps. But here we're interested in the temperatures. So what is the distribution and abundance of micro cold traps, given that we know that thermal gradients exist at these extreme spatial scales, small spatial scales, and that roughness increases with decreasing spatial scales. So you'd actually expect more cold traps and greater abundance at smaller scales. So getting on the surface is really key to finding all of the inventory of potential water reservoirs and reservoirs for other volatiles. And I mentioned correction of near infrared data sets that can be contaminated by thermal emission, like M-cubed. This set of measurements from L-CIRiS will help with that as well. So the instrument itself has 4 bands spanning from 7.2 to 14.3 microns, including 3 compositional bands and 1 broadband channel for doing the thermophysical investigation. We'll get panoramic images around the landing site in 180 degrees. So we'll see fully one side of the landing site from 3.6 meters all the way to the horizon. And at the nearest point in our field of view, the resolution is about 7 millimeters. So we get pretty high resolution close to the lander, and then that, of course, declines as you move away. And we'll see all the way to the horizon, where our pixel scale will be roughly similar to the Diviner footprint. And here's a rendering of the instrument, which is currently undergoing fabrication at Ball Aerospace. So I've described a little bit of the operations. Basically, we sweep plus or minus 90 degrees. Each scan takes several hours. And one of the innovative features of L-CIRiS is this 3-point calibration scheme with 2 different internal calibration targets. So we get very accurate temperature measurements across a huge range of temperatures on the surface. So one of the things that we're going to look for is these roughness effects. And here's some model results showing what a dramatic difference you see in these kinds of thermal images looking at the same surface from 2 different phase angles effectively. So with a solar azimuth of 180 degrees with the sun kind of in a line with your field of view, you see lots of shadows, of course. And then you look at the same surface at 0 degrees azimuth with the sun behind you, and you see a lot more hot surfaces. We can quantify this with the models and then compare that to the L-CIRiS data. And this will really give us a good constraint on how roughness affects infrared measurements, both in the thermal hour and all the way down to the 3 micron region that a lot of us are interested in. So we expect to get the first thermal infrared images from the lunar surface. I mentioned the thermophysical and roughness properties, and we want to link this to sample science as well, looking at the composition at these sort of nearly grain scale to compare to samples, and then understand how these micro cold traps affect the transport of water on the lunar surface. This also has implications for astronaut and rover trafficability, because we can constrain the thermal inertia of these regolith finds and other hazards and including rocks and those sorts of things. So thanks for your attention.